Yeah, my name is Farnik Nikakhtar. I'm a PhD student at UPenn. Today I'm going to talk about an ongoing project on the action angle variables of the slower streams in the FIRE2 simulations. This is an ongoing project with Robin, Nyayesh, and Neil. So to start, the idea of using the action angle space clustering or action angle variables to find the potential of the Milky Way. The general idea, just a review to general idea of what we want to do. We have the 6-dimensional phase space data, and so for star streams or stars in the star streams, we know that if we do this canonical transformation and go to the action and angle variables, we should get a constant action. But for doing this transformation, we need to have a potential. And the idea is like we can test different potentials and to see which one gives us the most clustered pattern. And this is the basic idea of testing or finding the right potential by using the action, the clustering in the action space. So it means that the correct potential maximize the clustering in action space. And we like Robin had a paper by maximizing the Kullback divergence, the KLD. We can test different potential and find the best or the most cluster actions. The 2 points or the 2 ideas that I want to talk about today, one is about using an alternative method of finding the clustering in action space using the 2-point correlation function, like in larger scale structures or galaxy clustering, that we can count different pairs of the stars of galaxies. Here, we want to use 2-point correlation function to find this clustering in action space. And another idea is about the conjugate coordinates of the actions or angle. So it's like we have 60 data, 60 information from phase space, and when we go to action space, if we just try to find the clustering in actions, it's like we don't use 3D information of the angle variable. So the question is like, is there something else in angles that we can use to find a better potential or something like that? Oh, sure. Thanks. So yeah, the idea of the 2-point correlation function is like when we define a metric in action space, it is the simplest metric that we can define. It's a diagonal metric, but of course we can see the correlation between the off-diagonal terms of JR, J phi, and JZ by having the covariance matrix. We can define a correlation function, like the data pair divided by random pairs. And so from that correlation function, we can define a likelihood. And by maximizing the likelihood, we can see in which space or in which potential we can get the best or the most clustered or the maximum of this likelihood. This is the results of Tiani Yang's paper, Nyayesh students. And they found that the circular velocity that they get from maximizing this likelihood, you see that there is a good or consistent circular velocity with their results of the Gaia DR2 data. So this is one idea. Another that we used, or that we tested this idea on the FIRE simulations. This is, for example, for one of the M12I simulations, and we tried to. They used power law model. They fixed the potential of the bulge and the disk, and they used the power law potential for the dark matter halo. And so they have just 2 free parameters. But basically, we can use whatever we want for the potential model. And so we tested that idea, and the circular velocity that we got was also consistent. And that is just the qualitative results of the reconstructed potential and the true potential of the simulation. Of course, the potential from the model has an error bar that we need to put on to see how well it works. Another idea is about the, one interesting point, for example, about this KLD and, so one thing about this KLD, it's like it's equivalent to this 2-point correlation function, the likelihood that we have here. It's equivalent to the KLD divergence that PFL used. Mathematically, they are equivalents, but when we want to use, for example, 2-point correlation functions, one advantages that we have is like we don't need to identify the star streams first. So we can just apply or measure the 2-point correlation function on all the sample. We don't need to first find the streams and then, for example, find using a kernel density to estimate the density of the streams. So here from the star streams, from the FIRE2 simulations, we looked at the some of these streams from Nant's catalog. You'll hear about it probably in this afternoon non-stack. We see this is one of the streams from the, I think, M12F or M12I, and this is the J space of JR, J5, JZ of that stream. But also it has, if we look at the angles, we can see these parallel lines in the angle variables. So we know that we can write the angles with these Hessian matrix that we have. And if we diagonalize the Hessian matrix, it gives us one of the, you can see one of the eigenvalues is much larger than the two others. And this stream with the stretch along the eigenvector of the largest eigenvalue, which is the slope of this line. And we tested that the slope of this line or frequencies, the slope of the frequencies is very sensitive to the symmetry axis of the potential. But the action clustering is more sensitive to the amplitude of the potential. And so the idea is like we want to find the slope of these lines and to see how we can define a clustering pattern in this space, in the angular space. One idea is like we can. This is one stream, and these panels are the angle, 3D angle variable. And so if we use, you'll hear about this half transform technique from Nan this afternoon. But if we use half transform technique, like if we try to detect these lines in these 2D panels, we can unwrap this stream in theta. These are all these parallel lines in the angle spaces because angles have like periodic boundary condition. So we can basically unwrap the stream, and if we have theta from -infinity to +infinity, we have just one single line in the angular space. And so, but in 3D, it's more tricky if you want to use half transform in the 3D space. And the idea that we used was like finding the eigenvector of the largest eigenvalue from the Hessian matrix and rotate all of the these initial coordinates to this new coordinate and project all the stars to this plane, which gives us something like this for all of the, for example, the angular variables of one stream. And what we are working on right now is like instead of using just actions, we can use action plus angular space clustering, these 3D space plus that two new plane that we have, and we project all the stars along. And so we can, if we define a new metric in this 5D space, we can write a 2-point correlation function and try to maximize this likelihood and getting a hope to get a better constraint on the potential. But we can also use like having a pipeline, and instead of making a likelihood, we can just use the KLD again on these new these 3D actions plus the 2D angle space that we have. Yeah, thank you so much. That's
What do you think the prospects are for applying this kind of technique to like satellite galaxies in the Milky Way, trying to pin down their potentials?
You mean if you want to look at the action angles of the satellite galaxy instead of the streams? So I think the action variables there are still a cluster. We can see a cluster in the action variables, but for the angles, I think they shouldn't be something like these parallel lines, and we should see also clustering angle variables. So basically, we can. I'm not sure, but I think we can use, for example, this action plus angle crossing, or putting more constraint, some measure, or defining a measure in angles for satellites to maximize something, a KLD, or a likelihood to find the potential.
And how much does like observational error affect that? Because like obviously the further out you go, larger proper motion error, larger
Right.
everything errors.
Yeah, one idea that using this 2-point correlation function idea in Tian's paper, they reported, for example, the effect of the observational errors on their results, and so they had some systematic errors because of the spot, yeah, here. And so one idea of using this, applying this method to the Fire2 simulations was like trying to understand the systematic errors that we have from observational parameters or variables.
Farnik, I love the angle work. That's so fun. I hadn't seen the last bit, right? So now I've lost my question. No. So have you tried doing this just with random samples yet in the fire simulations to see what it looks
random
like?
stars?
Yeah, in a random, like in a mixed halo yet of the fire simulations. Just curious.
No, we haven't. But I think one point about this 2-point correlation function idea that first we started to think about and work on was like this point that we don't need to identify star streams first, and so we can just apply on a whatever we want on a random sample. So, but I haven't checked those yet.
Yeah, I guess I was wondering, just even visualizing in the correct potential what these projections look like for a fully random sample would be really fun. Yeah. And then Carrie's point, of course, I agree with too.
Yeah, so I have a very basic question, like, so why is it that the correct potential maximizes action, like clustering in the action space?
It's like in the dynamical system, when we write, for example, the Hamiltonian, the orbit of these stars have the same features or have same properties, and when we take this canonical transformation and we go to action and angle variables, we can like mathematically see that it gives us a constant in the action variables.
So I had a question about this Hessian matrix. So you showed that it has of the 3 eigenvalues, one of the eigenvalues is much larger than the other 2. Is that always the case for the correct potential? Because it doesn't seem very intuitive to me why that would be the case.
For the star streams, yes, I think.
Okay.
And but to give more intuition.
Is that the case for most of the potentials we know of?
For example, I think, yeah, if we write, for example, that if we use the right potential for star streams, I see what you mean by your question, but I don't have an exact answer. But it's really interesting. I need to think about it more. But for example, for the satellites, I think I haven't checked, but I think the value of the amplitude of the eigenvalues of the Hessian matrix should be almost the same.
Okay.
Not one is larger than the others. But for stellar streams, we see that one of the eigenvalues is like 100 times larger than two others.
Okay, so it depends on your system, what will happen to the Hessian matrix.